This video documents the experiments for the paper, a complementary approach for robust and safety-oriented visual tracking via near-infrared and RGB-D cameras for safe physical human-robot interaction. In this work, we mainly carried out two experiments for comparing the tracking performance of two vision-based systems, as well as testing a proposed complementary approach for leveraging their strengths to track the movements of human co-workers within different shared and collaborative environments. The goal of the first experiment was to compare the performance of two vision-based systems for tracking key points on the human co-worker body around the collaborative workspace of a robot executing 3D tasks with desired, nominal velocity profiles. One tracking system employs an emit-race near-infrared camera for detecting reflective marker patterns on conventional, off-the-shelf safety vests. The other system is an open-pose tracking setup employing an Intel RealSense RGB-D camera. The robot is the Franca Emica Panda tactile robot arm, which was commanded to perform linear and triangular motions in its 3D reachable space. A reflective marker mimicking a mini safety vest was attached to the co-worker's wrist, making it possible for the emit-ray system to track its movements. The co-worker was asked to grab a rigid handle firmly attached to the collaborative robot end effector while the robot was moving. The estimated movement of the wrist point from the two visual tracking systems was compared against ground truth datasets recovered from the robot's proprioceptive sensing and kinematics. Multiple runs were executed by the robots for the two 3D motions, such that some statistical insights into the position tracking errors of the two tracking systems can be obtained, as reported in the paper. The goal of the second experiment was to demonstrate how the tracking outputs of the two visual tracking systems can be used in a complementary fashion to gain most of their advantages and avoid their shortcomings. For this, two mock-up physical human-robot interaction scenarios were investigated. Specifically, we studied the activation of the safety filtering of robot motions by the Safe Motion Unit, based on the complementary approach for fusing tracking data and dynamically defined collaboration regimes for mere coexistence and close collaboration. Those interaction regimes were defined as shown. The exemplary robot task used for demonstration was a pick-and-place task typical within automated intralogistics warehouses. The emit-race near-infrared tracking system monitors whether any human coworker entered the shared workspace. In such a case, the SMU scales down the robot task speed limit to a safe coexistence limit based on the distance information of the closest human body to the robot end effector. The open-pose RGB-D tracking setup monitors if at least one human coworker enters the collaboration region. Then, the SMU scales down the robot task speed limit further to a lower, safe collaboration limit based on the distance information of the closest human hand to the robot end effector. Those physical interactions were demonstrated in the two considered working environments with stable and unstable lighting conditions, as shown next. Initially, the robot moves with the nominal task speed. If a coworker enters the robot's reachable workspace, the Safe Motion Unit then immediately reduces the task speed limit from maximum to safe coexistence threshold. When the coworker's hand gets closer to the robot end effector, the Safe Motion Unit reduces the task velocity further to a safe collaboration threshold. As soon as the coworker's hand moves away from the robot end effector, or vice versa, the Safe Motion Unit relaxes the safety constraint and retains the coexistence threshold. Finally, the maximum nominal task speed is recovered as soon as the human moves away. However, the open-pose RGB-D system loses tracking momentarily if lighting conditions change. Meanwhile, the emit-ray system, thanks to the integrated near-infrared sensor, continues tracking as expected. Thus, the proposed complementary approach offers a robust, reliable tracking solution for safe physical human-robot interaction in different working environments, even under varying lighting settings.